Okay, so I'm going to go through my assumption checking for my models that I've created. So multicollinearity is our first assumption to check for points. Now, all I did was use essentially a correlation analysis built into R. It's called IMC diagonal. And what it does is it checks multicollinearity in the data. So it checks each pair of stats and sees if there's collinearity, which means they're collinear or have high correlation, which can throw off your model massively. And as you can see, if there's a 0 anywhere, collinearity is not detected by the test. So as we can see, we have significant evidence to show that there's no multicollinearity present in these. Now our linearity assumption is sort of a bit more subjective. So we have to look at a residual plot versus our predicted values, our fitted values for this. So as we can see, there isn't really a pattern to this data. It seems reasonably randomly distributed. It seems reasonably distributed between the upper and lower half of our residual plot. However, I still think I will, and as I did lower, I'll apply some transformations to this data to see if we get any better results. But this, isn't enough to show that it's not linear. So we're going to keep going. So now we need to check our homoscedasticity. Now, homoscedasticity is essentially equivalence of variance between in our interaction term, or between all our terms in our interaction model. So if I run this guy, we'll see the residual plot is reasonably randomly distributed. Though there is kind of a fit curve there, it still seems, there's no wedging or anything like that. Now, a secondary test we can look at is the BP test, the Bruch-Pagan test. And since our p-value is 0.21, this doesn't give us enough information or enough evidence to reject our null hypothesis. And in this case, the null hypothesis is that the variances are equivalent. So we pass our homoscedasticity assumption here. Now for our normality assumption, we do what's called a normal QQ plot, and we see how close to linear the residuals are on this QQ line. So as you can see, it's reasonably linear. Just from a look, it's reasonably normal. And we'll just do a Shapiro-Wilk test, which just tests for normality on that. And since, again, our p-value is 0.3775, we fail to reject the null hypothesis, which in this case is that the data is normal. So all assumptions are valid in this case for the most part. Now moving on to save percentage. We will do the same checks. So multicollinearity, we check. And it appears as though there is no multicollinearity, which, isn't the only assumption we make here. So our linearity assumption, again, this is up to interpretation. I personally believe there's not really a pattern here, and they're reasonably distributed. However, I'm still going to try a couple transformations to see if this helps anything. Now we're going to check our homoscedasticity assumption, which is, again, equivalence of variance. So I usually just run the BP test. As you can see, there's no wedging really at all here for this. However, and our BP test is the p-value is 0.321, meaning, again, we fail to reject our null hypothesis, which means that we believe the data is homoscedastic or has equal variance. Now for our normality assumption. So I'm going to run this, and we're going to look first at the QQ plot. Now, it looks oddly similar to our other QQ plot. However, our Shapiro-Wilk test shows that our p-value is actually quite low, which is below significance, meaning that we reject our null hypothesis that this data is normally distributed, which can sometimes be sort of a killer for your model, but other times it's not the worst. So I'm going to try some variances or some transformations to normalize this data, and we'll see how this goes. So yeah, so let's move on to the transformations I tried. So since we have failed a few assumptions, we're going to try some transformations. So essentially I just tried your typical square root transformation, log transformation, and reciprocal transformation on points to see if I could get it to be a little more linear. Overall, I really don't think it did much. I'm not going to run this because it will take a little while. It didn't really do much to change. It didn't improve our assumptions by much, so I just left it as it was. However, you guys can run my model and see, and maybe you guys believe differently. Again, this is really up to interpretation. Now, for save percentage, I really wanted to try to get the data to be normalized. However, none of these really improve the normality by that much. So I will show you, I believe, if I Shapiro tested on the arcsine transformation, I believe that was our best performance for normality. Let's have a look here. Yeah, so we got a p-value of 0.0006. So almost, well, actually not really almost there. We're still rejecting our null hypothesis pretty massively here that the data is normal. I still tried to predict because, you know, that's fun to do. And if we're within, if we're sort of predicting in this range, we're sort of predicting in the range that, like, from kind of this area to this area, it's not going to be the worst performance. So we'll have a look at that. Again, you guys can go through my code and look at, I just ggplotted the fitted and residual values for all of the transformations I did, and just looked at the results. So actually, like, we didn't really get much of a change as far as linearity goes. There's a bit of performance increase, but not a ton. So again, you guys can have a look through that. If there's anything that, I don't really think there's anything that's too complicated here. So, finally, I'm just going to run you guys through my predictions. I took Connor McDavid's stats from 2018. He was the leader in points in 2018, and I ran it through to predict. So using his shooting percentage and his minus from last year, I predicted his points. Oh, that won't run, sorry. So his actual points scored last year were 108. This predicts them at 80.495, which I expected. It's not a very robust model. It does have a high R-squared value, but it does not. I guess this kind of shows that the data really isn't linear, and it's kind of tough to use this as a predictive model. Now for save percentage, I used Andrei Vasilevsky's stats from 2018. His save percentage was 0.92, and his number of saves were 1,908. He played 65 games. He had a goals against average of 2.62. So if I run that prediction, that predicts it at 0.9186, which is quite close to 0.92. So it's actually a better performing model. So as we can see in this case, the data not being normally distributed actually isn't that big of a deal. Now I'd like to do some more in-depth performance evaluation of this and really expand the evaluation. It's pretty primitive right now as far as the analysis goes. This was more just a top to bottom from scrape to analyze data mini project. So this is where I'm at so far. But if you guys have any, if anybody who's watching this has any comments or questions or anything, my information's in the bottom of this video as well as on my website. So have a look, and thank you, and have a good one. Take it easy.